Yeah, I want to give you now a short overview about that, what we will do in the next period. So I do not want to explain too much on the recent work in our focus area. I want to focus on the next period. I also want to introduce my vice chair. This is Esan Fovetan from Denmark. Unfortunately, he could not be here in this meeting and also in the meeting before. Maybe some of you remember that my last presentation was, I think, starting with the same slides as my last GGOS presentation. And because our idea was to set up a definition of space weather, and I think it's very important to have an idea what we are actually dealing with. And therefore, and since there is no official definition of space weather available worldwide, so we thought then we do that by ourselves, and we set up this, what is written here. I do not want to repeat that here again, because it is really very complicated. And therefore, we got then some criticism that this is maybe too complicated and not geodetic enough. And therefore, we will change it again. And then the next GGOS meeting will start again with this slide, but then with a new definition. So this maybe starting with. So then again, a short introduction, what we are doing. We have a different kind of input data. The idea of this focus area is that we bring our space geodetic data together with solar and sun observations. This is shown here on this slide. Somehow, here's the sun, here's the Earth. Here are some solar missions. We have on the one hand side the stereo missions, which are observing the surface of the sun and also the surrounding of the sun. Then we have here in the center this so-called Lagrange point, where some satellite missions are active and they are observing the solar wind, the magnetic field, and some other important quantities. And furthermore, we introduce, besides these missions, then also some indices, some solar geomagnetic indices. You may know the F10.7 index, the KP index, which is reflecting the magnetic field and so on. And then in the last part here now, we have now our space geodetic observation techniques, which are in the surrounding of the Earth, okay, of course, and this all needs then to be combined. And this is really a big challenge. And this combination and of all that data, but if we do that, then we have really an improved monitoring of space weather events. We can set up forecast strategies. This is nowadays mostly done by machine learning processes, but again, it is a big challenge. And this is part of our work, and it is an important step of that, what we are doing in the focus area. We have a setup of objectives here. So these are the updated objectives. So these are valid for the period now from 2023 to 2027. We want to develop an improved ionosphere and plasmasphere model. So this is also new that we have now the combination of ionosphere and plasmasphere, because it is meanwhile clear that there are situations, there are times where the plasmaspheric part is very large. So up to 50% of the complete effect of the electron density. So that means we have to deal with the ionosphere and the plasmasphere together, and on the other hand, they are strongly coupled. Then in the second point, we have the thermosphere. The thermosphere is a very important for precise orbit determination. It's the largest part in the equation of motion for satellites, and therefore especially for LEO satellites, strongly coupled to ionosphere and plasmasphere. These coupled processes are then here shown in point number 3. MIT is magnetosphere, ionosphere, thermosphere. The magnetosphere is the sphere around, or we could say all these different spheres, ionosphere, plasmasphere, and thermosphere are embedded in that. So an improved understanding of space weather events, monitoring of geodetic and non-geodetic observation techniques. So that, as I said, needs to be combined so that we get then this improved understanding. So the electron density is for ionosphere and plasmasphere the most important quantity. For the thermosphere, we have the neutral density. So these are the two strongly coupled quantities. Yeah, these coupling processes are already mentioned. And finally, then this improved understanding of space weather events is the fourth objective. So coming up to the new structure. So we also replaced our old structure from the first period a little bit. I have this here on this slide, also maybe rather complicated. I do not want to go in all the details. So what we have on the top, we have now these three boxes where we have together then all the observations I already mentioned. We have the space geodetic observation techniques, GNSS, altimetry, DORIS, IRO. Then we have the solar observations from these ACE and Discover from at the Laplace point. We have the stereo satellite, we have these indices I mentioned. And then we have, on the other hand here, a technique, namely the precise orbit determination, which brings then the thermospheric part into play. Here also then satellite laser ranging is included. Then, of course, also GPS and DORIS again, accelerometry is included. So this is the setup of all the observations. Then in the center, we have now that what we are doing in the space, in the geodetic space weather research focus area. We have here ionosphere and plasma modeling, thermosphere modeling, and the coupling processes. Magnetosphere, as I said, is that where everything is embedded in. And then we have in the last, or the bottom part now, the products. The products we want to provide, or they are already provided. These geodetic products are, on the one hand side, the vertical total electron content. You all know maybe these global ionospheric maps, so the GIMS. Then we have the electron density itself. So this is actually the distribution of the electrons. If we would know that, then we have everything solved. And we have then the neutral density of the thermosphere. So yeah, so that all is realized by the introduction of 4 joint study groups. These 4 joint study groups are listed here. We have joint study group number 1, understanding ionospheric and plasmaspheric processes. This is related or connected to IAG Commission 4, and then the subcommission 4.3. Here the chair is Fabrizio Prol, and David Themes is the vice chair. The second joint study group is thermosphere modeling, improvements and applications. There Günter March is the chair, and Armin Corbin is the vice chair. We have space weather monitoring and prediction. Aisha Liu is the chair, and Benedikt Zoya is the vice chair. And finally, the atmospheric coupling studies, which is a study group which is actually led by ICCT. So therefore, it is not primary in our focus area, but it is then a study group we count as a part of our study of our focus area. And there, Andres Calabria-Eiber is the chair, and Binod Aydikari is the vice chair. I do not want to go into too much detail. I only want to say something about that, what Joint Study Group number 1 wants to do, or the objectives. We heard a presentation from Fabrizio in the meeting before, so actually most of you maybe have not heard that. It was on Tuesday, where then the modeling of the ionosphere and plasmasphere. So as I said, this must be seen in a combined way now by different approaches. And this is then also one of the objectives, also using new instruments, the 3D modeling, and so on. So then things are done partly. I cannot now go into detail related to all these issues here. One important thing is also that a special issue is set up in advances in space research. Joint study group number 2 is related to thermosphere modeling. So here an improved thermosphere modeling is aimed on for better consistency is necessary. Also, the different objectives are listed here. I just want to highlight, because I will come back to that later in my talk, that here in the last point we have the word climate change, or the 2 words climate change, and the use of improved thermosphere models and observational data sets to advance the study of thermospheric variations in the context of climate change and space weather monitoring. So this is something which is very important, because we can see from thermosphere modeling also something related to climate change, and I will come back to that in a few minutes. First, I want to show you that figure here, where we see now different thermosphere density functions, which are computed or estimated by different algorithms and models. And if you now look at that, we have IGG. This is a computation which was done in Bonn. Then we have Toleos. This was done from ESA. Then TI-GCM is a physical model, and Yakia Baumann and NLMSys are two empirical models. So if you then look at the variation of these densities, then you see also how they are very different. So, and they are partly 100% different. So, and if you then introduce that into a precise orbit determination, you would directly see that that has an influence of the results for the satellite positions. So, and therefore, you see how important it is that these models are improved. Yeah, I come now to another point. So we had in the last 3 days here in the same building, in the same room, the GGOS topical meeting on the atmosphere. There was a motto. The motto was bringing together science excellence to integrate geodetic and geophysical technologies for a comprehensive monitoring of the atmosphere. Atmosphere is meant here as troposphere, stratosphere, mesosphere, thermosphere, ionosphere, plasmasphere, and then also the magnetospheres and all the components, all the subsystems of the atmosphere. So, and we had many presentations here. So I have a short overview about statistics around 85 participants. We had almost 40 oral presentations and 20 posters, and very interesting presentations and posters. Here you see the different topics we have on the besides the opening. We had then magnetosphere, ionosphere, plasmasphere, and thermosphere. This is how this is coupled. So this is one very important topic of atmosphere modeling today. Then ionosphere modeling applications, climate applications of geodetic atmosphere parameters, geohazard monitoring, geodetic methods for water vapor monitoring, severe weather monitoring with geodetic techniques, and atmospheric modeling based on artificial intelligence. And in brackets, you see always the number of presentations and posters. So, and yeah, I want to give a short summary of a presentation I give myself here in that meeting. It was in the opening. It was a presentation together with my vice chair, Isan Fortan, and it was related to these EGVs, the essential geodetic variables. Laura already mentioned that in her presentation. And here we want to focus on that, what is related to our. So that means the title was Possible Definition of Essential Variables for the Upper Atmosphere in relation or from the perspective of the focus area geodetic space weather research. So, and I introduced a little bit about EGVs, not very much, and I do not want to repeat it. I have no time to do that here now. I think later today there will be a presentation or talk about that from Thomas Gruber, and he had also presented together with Detlef Angermann and Laura Sanchez a white paper about that. And what my part of what I want to show you now here, how do now these essential geodetic variables fit to that what is done by the climate community. So, and I can do that only for my field. So therefore I restrict myself now for one single EGV, and this one single EGV is the EGV number 12. Now neutral atmosphere and ionosphere. And how is this related to that, what the climate people are doing? So here you see the list of 18 already selected, not finally, this is all in discussion and review. So, but finally we have here this EGV number 12. And each EGV in that list has some specific geodetic products, water vapor content, thermosphere density, and global atmospheric map. So these electron density are these products here. So that means now, That means now, if I remind you to these products, what we had here, then we have the vertical total electron and the neutral density of the thermosphere. And then I compared that with what from the climate community is set up here. We have the so-called ECVs, so the essential climate variables divided in the atmosphere, land, and ocean part. And if we now compare that, then we see that water vapor, for instance, so in our EGB12 is also here, but it is seen as a climate variable. So therefore, we could then summarize that water vapor is on the one hand side in geodesy a product, but in the climate community is here seen as an ECV, so as a essential variable. The question, is there any consequence? Do we have to change that? Whatever. This is there only written there. And another point I want to indicate is that we had different parts which are covered. We have here the surface atmosphere and the upper air atmosphere in the climate community. And if I show that here in that figure, then this is more or less, or actually it's the same as troposphere and stratosphere. So that means now that in the climate studies, actually atmosphere is seen as troposphere and stratosphere. However, in our case, we have much more. Yeah, we have the complete atmosphere, including mesosphere and so on, until plasmasphere and magnetosphere around. So therefore, we could say that in the geodetic, we distinguish between actually lower, mid, and higher upper atmosphere, and then we can conclude that in opposite to the ECV, so the climate variables, our EGB12 considers climate signals also from the mid and the upper atmosphere and has therefore more information. That is then again something what we could where we could make some consequences from or not. However, just this is just a paper where it is shown how that climate change is also in the thermosphere visible, that is also in the ionosphere visible. There's another paper which Lea Zeidler and Armin Corbett and others, so we actually did that at TGFI and in Bonn. I do not want to have the time now to go to that. Maybe last slide now is that a list of some challenges. So on the one side, geodesists use ionosphere or saw ionosphere as an error source, which has to be corrected. On the other hand, the fact that almost all geodetic observations are influenced by the atmosphere, that all these observations include or provide valuable information about the state and dynamics of the ionosphere and plasmasphere. And the propagation of electromagnetic waves, is depending on the charging state. The POD, as I said, is depending on the thermospheric density. And since the geodesy has a long experience with development of techniques and model approaches. And now the last 2 points are, in my opinion, very important because Earth system modeling, what does it mean? We have different components, different subsystems. We have atmosphere, we have oceans, we have continental hydrology, geosphere, and so on. Laura also showed that at the beginning. So, and if we do geodetic Earth system modeling, then we also look at the interactions between these spheres. So this is now the same what we have to do in the atmosphere alone. So atmosphere is one of the subsystems here. But it is then consisting of that what I showed you, troposphere, stratosphere, and so on, up till thermosphere, ionosphere, and plasmasphere, and the magnetosphere around. So that means also here, we need to consider all these coupling processes. This is what we do here, and what I think must be done in future in a much more extension, because this is important, because we need now very high, precise models for ionosphere, for the new applications, for new topics or applications, namely, for instance, autonomous driving and precise precision farming. And therefore, you see how important such a very high, precise coupled modeling is. Okay, then I will stop here. Thank you very much for your attention.
Questions or comments? I think this focus area is not only important to improve Earth system monitoring, but also it has a very economical impact on satellite missions. Most of the activities on Earth are based on satellites, and if the sun gets angry, the satellites have problems.
This is another point I did not mention now here, but you're right. This all has to be considered too. Also, re-entry processes and so on.
Thanks for your presentation, and thank you for raising the issue of linking the essential geodetic variables to the essential climate variables. And you may see some of you in my presentation on integrated water vapor. We started from what climate system is asking, what are the requirements of climate system, and we tried to give an answer to these requirements, but we have seen that there are still open issues. The uncertainty, how they define the uncertainty, how they define the stability. So this is, and also for the horizontal resolution, and something that we have to do regarding the network maintenance, sustainability. So I'm very much in favor of this, and thank you for asking.
Welcome, you're welcome. Thank you for your comment.
Yeah, I'm only very happy with your initiative.
Yeah, welcome.